This is Darif Seitz. This tutorial is about linear functions. Linear functions and non-vertical line linear equations in two variables are closely interrelated topics. The solution set of every such linear equation is a linear function, and every linear function is the solution set of such a linear equation. In this discussion, because of the close interrelationship between linear functions and linear equations, we'll be looking at both of them. The first thing that we need to talk about is the concept of the slope of a line. Slope is a measure of the left to right inclination of a line. If a line rises from left to right, it has a positive slope. If it declines, it has a negative slope. In this picture here of the railroad crossing, right here we have one of the bars going from left to right. The bar is rising, so that has a positive slope. This bar here going from left to right is declining and has a negative slope. If it is horizontal, that is flat or level, it has a zero slope. For example, the tracks here are horizontal. There's no slope, a zero slope. If the line is vertical, its slope is said to be undefined. We have some poles here coming up vertical in the background, some poles. Their slope is undefined. Let's take before we take examples, to get a measurement of slope, we have a formula that's used. The slope of the line that contains 2 points, x1, y1, and x2, y2, is given by the following relationship. The slope is the ratio of the rise over the run, which is the same as delta y, the change in y's, over delta x, the change in x's, or simply in terms of the points, the difference of the y coordinate values divided by the difference of the x coordinate values. Remember here, these subscripts are just part of the name of the variables. They have no mathematical meaning like an exponent. It does not matter which of the 2 points you take as the first one and which as the second one, as long as you compare the y's in the same order as you compare the x's. We're looking at a ratio here of the difference in the y's over the difference of the x's, and that gives us a number, the slope. Now for some examples. Here we have some points and some lines through them. We have different colors on the lines. There's a line that is increasing, the blue one, from left to right, should have a positive slope. The green line is declining, should have a negative slope. There's an orange line, flat, should be horizontal, zero slope. And a purple line, vertical, should have an undefined slope. Calculating the slope, first for the blue line, we take the 2 points on it, which are 1, 2, and negative 3, 0. Take the difference of the y's here, 2 minus 0, and the difference of the x's is 1 minus a negative 3. Remember, the minus a minus is a plus, so that's 2 over 4, or 1/2, has a slope of 1/2. The green line between negative 2, 3 and 1, 2, calculating the slope, difference in the y's over the difference of the x's, we get negative 1/3, and indeed it does have a negative slope. The orange line, the 2 points on the orange line, notice that their y coordinates are the same. That's true of any horizontal line. The y's will all be the same. So taking the difference of the two y's, we'll get 0 in the numerator, and the whole fraction becomes 0. The vertical slope, notice that 2 points on the vertical line have the same x coordinates. That's what makes it a vertical line. And when we use the slope formula, we'll be getting 0 in the denominator, and division by 0 is undefined. It's important to understand that slope is a ratio, but it's comparing actually the relative rate of change between an independent variable, the x in our case, and a corresponding dependent variable, the y. Let's consider some examples. First example, consider the simple statement that a vehicle is traveling at a rate of 60 miles per hour. We have a formula that most people are familiar with. Distance is rate times time. Dividing both sides by t, we can rewrite this as rate is the ratio of distance over time. So in our problem, the rate is 60 miles per hour, and 60 is 60 over 1. So the ratio of the distance to the time, the delta, the change in d's over the delta t. Delta is a mathematical symbol that means the difference or the change. So the change in distance is 60 over the change in time of 1. That means each hour, the hours on the bottom, the vehicle advances 60 miles. And each advance of 60 miles takes 1 hour. Our next example, suppose 5 apples sell for $3. The dollars per apple ratio is $3 over 5 apples, is 3/5. Dollars compared to apples is 3 over 5. This can be rewritten in two other ways. It can be written as 3/5 over 1, or it can be written as 1 over 5/3. And looking at it that way, each apple, which is on the bottom, is worth 3/5 of a dollar. So if we have one apple here on the bottom, its dollar value is 3/5 on the top. And 3/5 of a dollar is 60 cents. Or, looking at the other ratio here, each dollar, when we have 1 on the top, is equivalent to 5/3 or 1 2/3 apples. Some very frequently occurring architectural lines are parallel lines. Parallel lines never intersect. The distance between them remains constant. In terms of slope, two lines are parallel if and only if they have the same slope. The if and only if, remember, means if they're parallel, they will have the same slope. And if they have the same slope, they are parallel. Here's an example of two lines, both with a slope of 1/2, 0.5. We can see the ratio of the rise over run is a 1/2 over 1, or 1/2 on both these lines, and clearly they are parallel. Let's also consider perpendicular lines, which also occur frequently in the design of things. Perpendicular lines intersect or cross at a right angle, a 90-degree angle. Two lines are perpendicular if and only if their slopes are negative reciprocals of each other. Let's look at this geometrically here. If we start at the origin and do a rise of 3 and a run of 5, we have a 3/5 slope on this red line here going between those 2 points. Notice that's the same as doing a run of 5 and a rise of 3. It does not change the ratio because the rise is still 3, the run is still 5. It does not matter which one you do first. As long as they both occur, you'll get the same ratio and the same ending point. Now, if instead we do a rise of -5 and a run of 3, we end up with this point down here. And again, it's the same as doing the run first and then the rise. And let's look at these 2 red lines. Well, they're line segments, but consider the lines through them. This triangle right here is a right triangle. Because of that, the sum of its 3 angles will equal 180 degrees. But we have a right angle right here, a 90-degree angle. That means that the sum of these 2 angles, alpha and beta, will add up to be 90, because 90 and 90 will give you 180. So alpha and beta add to 90. We have that represented right here, a little formula. This triangle down here, notice that we're dealing with similar triangles here. In fact, not just similar triangles, but actually the same triangles, just in a different orientation. This triangle right here is the same as this triangle right here. It has the same lengths for the sides. It has the same angles. All 3 sides are the same. Well, 2 of the sides we know are the same, and it's a right triangle, so using the Pythagorean theorem, the other one is as well. And we can see that it's just a transformation, moving things down a certain way. So this angle here is alpha, because it's across from the shorter leg, and this angle here is beta. If we add alpha and beta together here, this angle between these red lines, alpha plus beta, is 90 degrees. We have a right angle, and those 2 lines are perpendicular. And notice the relationship in the slopes. This one is a negative reciprocal of that one, and vice versa. And there's nothing special about 3 and 5. Any 2 numbers, you can use the same visual proof to see why it is that perpendicular lines, their slopes have this negative reciprocal relationship. Let's look at the concept of interchangeable forms. We'll need that momentarily when we look at the equations of lines. Looking at water, for example, we have here ice or snow. It's a solid form when it's frozen. The next here, water itself, the liquid form. And finally, steam. If we apply heat, indicated by these red arrows on the left, we can transform the water from the snow state to the liquid state, the ice to the liquid to the steam. And if we remove heat, which is the same as making it colder, with the blue arrows here, we can go back to the other forms. Each form is the same essential water. Water hasn't gone away, it's still there, but it's in a different form, And there's different usefulnesses, different utilities for the different forms. We can use ice for different purposes from regular water, and steam different purposes as well. They have different utilities, different functionalities, but we can go back and forth with the same water and change it into these three different states. We have the same concept. We look at forms of linear equations. There are three very well-known forms that are very useful. There are more than three altogether, but the main three have the same concept, that when we have an equation in one form, we can manipulate that equation to create an equivalent equation, an equation with the same solution set. It's in a different form, and the different forms have different utilities, different purposes, different strengths. The first form we're going to look at is standard form. ax plus by equals c, where a and b are not both 0. A could be 0 but not b, or b could be 0 and not a. The variables here are x and y because we're looking at solutions as ordered pairs of x and y's, which are points. And all the solutions will make up a line. There'll be points all aligned in a line. The a, b, and c are placeholders for numbers. Standard form is the preferred form when solving systems of linear equations, especially using the strategy of elimination by adding the two equations together or subtracting one of them from another. Two special cases of standard form occur when a or b is 0, which results in an equation with only a single variable, x or y. These cases correspond to vertical and horizontal lines. Here's an example of standard form. The blue line, 2x plus 3y equals 7, has both x and y. The red line, y equals 5, is a horizontal line. There's no x involved in that equation at all. The thing that represents the line is the fact that every point on it has a y coordinate of 5. Here we have a vertical line, a green one. X equal 2 is its equation. It's not a function. Vertical lines are not functions because when you ask a question for a given x, such as 2 in this case, you will get more than one answer. In fact, you'll get infinitely many answers, making it not a function. All the other lines are functions. But x equals 2 is a special line. We don't want to leave it out of our treatment simply because it's not a function. The second form, this is a very useful form, is the slope-intercept form, y equals mx plus b. When you have the equation of a line in this form, you can read right out of it, m is the slope of the line and b is the y-intercept, the height or depth on the y-axis where the line intercepts the y-axis. Look at this example here. Y equals 3/5 x minus 2. The slope is 3/5, that's the blue line here, and the y-intercept is -2. If we look at -2 on the y-axis, there's a point on the line. To get to a second point, we use the rise over run of the slope. We'll go up 3 and run or go over 5, and we get another point, 5, 1. The slope is positive. Another way to get that ratio would be to go down 3, and that's a negative rise going down, and then to go in a negative direction for the run to the left 5, we'd get our second point over here, which is also on the line. Either way, the ratio is a positive 3/5. Slope-intercept form directly converts to function notation by replacing y by f of x. Provided the line is not vertical, for example, y equals 2x plus 5, converts to f of x equals 2x plus 5. Here, the function name is f. This is the notation for the whole function notation. X is the independent variable, the one we'll ask questions on. All the x's make up the domain, the set of questions we're allowed to ask. And the answer, the second coordinate of ordered pairs, also known as the y-coordinate on the graph, is given by the formula 2x plus 5. So for any x, we just substitute in this formula to get our answer, our y value for our function. The third form of linear equations is the point-slope form. It's taken directly from the formula for slope, which is the difference of y's over the difference of x's. If you multiply both sides by the difference of x's, you get the formula. Y minus y1 is m times x minus x1, where here, again, x and y are the variables, m is the slope, and we're given one point, x1, y1 is the coordinates of that point, and we'll get this formula. A variant by adding y1 to both sides is this y1 plus m times x minus x1. This form is a convenience form that is useful when you know the slope and a point on the line. Here's an example. It says, find the equation of the line that has a slope of 3/5 and that contains the point 1/2. Using the second form here, we get y equals 2 plus 3/5 x minus 1. Looking at the graph of the line, we'll notice that the point 1, 2 is on the line, and with 3/5 slope from that point, we can rise and run and see another point here on the line. Let's look at a problem. Find the equation in standard form of the line that is parallel to the line 2x plus 3y equals 12 and that contains the point 1, 2. We're given a line and a point. We want to find the equation of another line, and we want to get it in standard form, that goes through this given point and is parallel to this given line. We're going to show two different solutions to this. Solution 1. This solution will show that the point-slope form is not a necessary form. We will not use the point-slope form in this, and even though we're given a point and we will have a slope. First, we must find the slope of the given line, because since the lines need to be parallel, they have to have the same slope. So the first part of our problem is to find the slope of the given line. We transform that, rearrange that equation, subtract 2x from both sides, divide everything by 3 to slope-intercept form, and now we know the slope is negative 2/3. And since our line has to be parallel, our slope needs to be negative 2/3 as well. We will use the slope-intercept form and write y equals negative 2/3 x plus b. We don't know the y-intercept. However, we do know one point on our line, and we're going to substitute that point for x and y into this equation we have right here. We substitute the 1 for the x, the 2 for the y, and we'll be able to solve for b. We'll find that b is 8/3. Plugging back in, we get the equation of our desired line. However, we were asked to get it in standard form, multiply both sides by 3, and rearrange the x's on the left, and we get our answer, 2x plus 3y equals 8. Let's check this graphically. The original line, 2x plus 3y equals 12. The given point, and here's our answer. It goes through the point and is parallel to the original line. Looking at the second solution to this, using the convenience form, the point-slope form, again we have to find the slope of the given line. We just repeat that here, -2/3. And then since we have the slope in a point, we can immediately use the point-slope form and write the equation here by putting the point in and the slope, multiplying everything by 3 to clear the fraction, distributing and rearranging, we get the same answer, 2x plus 3y equals 8. It's important to understand that this problem was a multi-step problem. We first had to find the slope of the other line, using the fact that our line was parallel to that. Then we needed to use the fact that we were given a point and write the equation of our line, and finally we had to rearrange it to transform it into standard form. That's shown here. Find the slope of the given line, find the equation of the line with that slope that goes through the point, convert to standard form. Since many math problems are multi-step problems, it is important to develop multi-step problem-solving skills. Some basic strategies that you can use to solve multi-step problems: draw a picture. You can take what's given and draw a picture, and when you see the picture, it will help you to use your visual thinking skills to get some traction on how to solve the problem. Then you'll have to plan the steps, your strategy, as we did in our example, of going through the multiple steps needed to get to the final answer. And a third important strategy here is to remember to use what you've been given. Most of the time in the problems you're asked to solve in the academic world, you will be given only exactly what you need and no more. And if you leave something out, it's usually a key piece. So we've talked about linear functions, there being lines, the fact that they have slopes, and they have some standard form, slope-intercept form, and a convenience form, point-slope form, and how to do some simple multi-step problem solving.